In this video, we are going to take a look at determining the area and arc length in polar coordinates. Starting with the area, we can calculate the area underneath a polar curve much the same way that we can calculate the area under a curve in rectangular coordinates. The formula for it here is, of course, a little more interesting than what we're used to. The area is equal to 1/2 the integral from alpha to beta of our polar function f of theta squared d theta. Okay, that can also be rewritten in terms of, because r is a function of theta, it can be written as r squared d theta. So one thing we need to make sure that we need to be concerned about is that theta is between, these are the bounds, so theta is bounded by alpha and beta. And also right here that the difference between alpha and beta has to be less than 2 pi. It has to be greater than 0 or less than 2 pi, in which most cases it is actually going to be that. So let's take a look at our first example of how we actually use this formula to find the area under a polar curve, or bounded by polar curves. So the first one, we have the polar curve r is equal to 4 plus 3 sine of theta, which is a type of a cardioid. Now the first thing that I would suggest that you do is go to Desmos and graph this. And you can even put in the bounds of integration here. And of course, we have our alpha and beta, and if we do beta minus alpha, we end up with pi, which is less than 2 pi, greater than 0, so it meets that requirement. Moving over to Desmos, here is what this graph is going to look like. So we have 4 plus 3 sine of theta, and I have just graphed it over the interval from negative pi over 2 to pi over 2. So we're basically looking for the area bounded by this curve over this interval. So it's just a matter of following the formula. So we have area is equal to 1/2 the integral from pi over 2 to negative pi over 2 of 4 plus 3 sine of theta squared. So as is always the case, a lot of this is just going to be algebra. So many of these next step is just algebra. So the first thing we want to do is square our polar function, and we end up with this. And of course, we're used to knowing what to do when we have a sine squared. We can replace that with 1 minus cosine of 2 theta divided by 2. So I put the 2 over here. And that's times the 9, so it gives you a 9/2. And then breaking that up into 2 separate terms, because now the 9/2, we can eventually combine that with the 16. We could do it now. I ended up doing it a little bit later. And once we get it to this point right here, now I'm actually able to find the antiderivative of that. So the antiderivative of 16 is 16 theta. The antiderivative of 24 sine of theta is negative 24 cosine of theta. Antiderivative of 9/2, 9/2 theta. Antiderivative of negative 9/2 cosine of 2 theta is negative 9/2 sine of 2 theta. And now we can combine this term and this term. And we end up with this term right here. And then we have the minus 24 cosine theta. And changing sine of 2 theta into 2 sine of theta cosine of theta gives us negative 9 sine cosine theta. And that is being evaluated from pi over 2 to negative pi over 2. So I leave it to you to actually do the plugging in of these functions to evaluate that. And again, you can either use your calculator, you can use Desmos, or you can do it off the top of your head, whichever works for you. And so we'll end up with these quantities. So we have 1/2 times 41 pi over 4 minus 0 minus 0. And then when we're plugging the negative pi over 2 in, we end up with negative 41 pi over 4 minus 0 minus 0. And so those are going to end up combining. And we end up with 84 pi over 4 times the 1/2. Gives us 42 pi over 4, which I could have reduced to, 21 pi over 2. But 21 pi over 2, I'm not sure why I didn't reduce that. And that would be our area. So the actual integration is pretty straightforward. The little tricks that we use to integrate this are tricks that we've learned previously. The only real new part is this formula for finding the area bounded by a polar curve. And of course, I have the little sketch over here, but I also graphed it in Desmos. It's just kind of handy to have an idea as to what the graph is going to look like. And of course, in this particular problem, we were only graphing from this area all in through here. So remember, we start at the pole and we work out. And we're finding all of that area. The second problem is going to be fairly similar to the first one. This is another type of cardioid. And so it's pretty straightforward. We have our formula. Area is equal to 1/2 the integral from alpha to beta of the polar curve, which is 5 plus 2 cosine theta squared d theta. And I actually graphed this in Desmos. So that would be this curve right here. That is a cardioid. And so we are finding the area of the cardioid from 0 to 2 pi, because I believe it says that it wants bounded by that curve. So sketch the curve and find the area it encloses. So we're just going to go the full from 0 to 2 pi. So plugging in, expanding the 5 plus 2 cosine of theta, we end up with 25 plus 20 cosine theta plus 4 cosine squared theta. Plugging in our formula here, we have 1 plus cosine of 2 theta divided by 2, which of course is going to come out and multiply by that 4, giving us a 2. And breaking that up into two separate terms, combining the 25 and the 2 to get 27, plus the 20 cosine, plus the 2 cosine 2 theta. And then we can find the antiderivative. So the antiderivative of 27 is 27 theta. The antiderivative of 20 cosine is 20 sine. The antiderivative of 2 cosine of 2 theta is going to be the sine of 2 theta and minus. And then changing the sine of 2 theta into 2 sine theta cosine theta once again. And then we can evaluate at 2 pi and evaluate at 0. And again, I'm saving most of that work for you to do. We should end up with 54 pi times the 1/2 gives us the area of 27 pi. And so again, what we're doing, just to enlarge this, we have a cardioid, looks something like this. And so when we're finding the area is we're starting at the pole and we're making little tiny sectors that start at the pole. And we're finding the area of each one of these sectors all the way around. And so as we make these little sectors smaller and smaller and smaller until the number of sectors approaches infinity, we have a formula using Riemann sums for the area of the polar curve. And of course, this is all explained in your textbook in more detail for those of you that want a more in-depth analysis of where these formulas come from, as always. Next one is a little bit trickier. We have r is equal to the square root of 1 plus cosine squared of 6 theta. Find the area it encloses. And I have no intentions of attempting to graph that function, so we're going straight to Desmos. And in Desmos, that curve looks something like this. Whoa, let's make it larger. Okay, so that's what the curve looks like, and we want to find the area that is enclosing. That's basically going to be the area within each of all of these many, many, many petals. Okay, so it looks something like a rose curve. Something like a rose curve. And back to our function. So it's actually quite an easy function to work with because, as we know, we take the function and we square it, and since we have a square root, they just cancel each other out, so we end up with the area is equal to 1/2 the integral from 0 to 2 pi of 1 plus cosine squared of 6 theta. And again, that's because we have the integral of r squared square root, or I should say it's the integral of the square root. Well, it's r, and then we're squaring that. Either way, we end up with just the function underneath the radical. So changing the cosine squared of 6 theta to 1 plus the cosine of 12 theta divided by 2, and distributing that 2 out and combining it with the 1, which is 2/2, we end up with this. Finding the antiderivative, we have 3/2 theta, and we have 1/24 sine of 12 theta. And then we want to evaluate that from 2 pi to 0. We end up with 3 pi times 1/2 would be 3/2 pi. All right, that is it for finding the area underneath or a polar curve or bounded by a polar curve.